so I'm going to tell you. And then, so a bit of history, then our methods, we tried to reconstruct estimates for the total biomass of all marine life as it would have been, 150 years ago in a pristine state, and then as well up to the present day. And so then I can show you what the pristine size spectrum looks like at the global scale, and finally, how humans may have altered this pattern. So what's the size spectrum? Let's see. What's the size spectrum? It's the story begins, I guess, 50 years ago, when maybe a bit earlier, when Ray Sheldon and his collaborators boarded a research vessel and started hauling buckets of water out of the ocean and passing it through a Coulter counter, which counts the size and the number of different particles, mostly plankton. And so this led to a magnificent paper, now 50 years old, where Sheldon et al. Hypothesized that to a first approximation, roughly equal concentrations of material occur at all particle sizes within the range from bacteria to whales. So how did they come up with this crazy bold hypothesis? They did a circumnavigation of the Americas, and at each site, they got buckets of water, put it through the Coulter counter, and constructed plots like these on the right-hand side. And so based on these measurements, they made a very big, bold hypothesis, bacteria to whales, and that's shown here. They were focused on very small things like plankton, things that could fit through the tube of their Coulter counter, but then the basis of their hypothesis was sort of this thick black marker scrawled on the page. At least they used a ruler to make it straight, but that's kind of where the hypothesis, as far as we could tell, has sort of languished. And so we just wanted to kind of confirm this with more up-to-date data. So, I'm being a little facetious here with the thick black marker. Obviously, this is a classic paper. It should be recognized as such. I don't think it is, but anyway. So 23 orders of magnitude, that's what we're talking about when we say bacteria to whales. So a small bacterium to the size of a blue whale, that ratio of mass is about the same as, say, you to the mass of, I wonder if you have a sense of what that might be, because it really is astronomical. It's not the mass of all humans on Earth. That would only be about 10 orders of magnitude. It's not the mass of all of Earth's water, say, that's about 19 or 20 orders of magnitude. It's the mass of the entire Earth, right down to its molten core. So that's what we're talking about with this hypothesis. So let's get to our study, estimating marine biomass. This started out when I was a postdoc in Barcelona in Eric Galbraith's lab, where I met Ryan Hennigan, who's also a postdoc at the time with a strong modeling and statistical background. And I suggested, let's try to test this hypothesis. That was now almost 4 years ago. And we quickly realized just how hard it was going to be. Very different taxonomic groups require very different estimation methods. Whales and large fish can individually range over the entire ocean. And so the only scale at which this hypothesis can kind of really be tested is the entire ocean. And then we wanted to do this in the absence of human interference, which makes it even harder. We have to sort of reconstruct biomass estimates from before industrialized fishing and whaling. So that was the challenge. Maybe some of you are probably thinking, well, it just can't be done. And maybe you're right, but at least something can be done to the best of our ability, kind of updating what Sheldon had done. And so we then recruited Yinon Baran, who had just come off writing a paper on the biomass of all major groups on Earth. And so we thought he could help us locate data. He could kind of sanity check our results. And I should just say, if you ever get the opportunity to work with any of these guys, you should jump at the opportunity. So we basically had to kind of divide our methods into 5 separate kinds of methods tailored to the available data. that we thought we had. And again, we wanted to estimate pristine biomass. And so we needed to make certain simplifying assumptions. We were only considering sort of direct human impacts rather than indirect, such as maybe habitat modification or changes in feeding relationships and so on. And so we assumed bacteria and plankton groups were largely the same, both pre-industrial and today. And so this is a bit tedious, but it's kind of necessary because you already all know about the intro, you know about the results. Sheldon published them 50 years ago, so this is kind of the only thing that might be different. But so for bacteria, we used 50,000 water samples in different locations, and then we correlated those to environmental variables so we could interpolate over the entire ocean. For phytoplankton, we used satellite imagery of chlorophyll with empirical equations to convert chlorophyll to phytoplankton biomass. For zooplankton groups, there's several of them. We used 200,000 water samples and similar statistical techniques as for bacteria to again interpolate over the ocean. And for fish now, the task was much more difficult. Not only do they migrate over vast distances, they school, they actively escape capture. You need large nets over large areas to obtain representative samples. But more problematic, we were trying to reconstruct their biomass from 150 years ago. So to do this, we used two independent process models. Both have been previously published and they were constrained by harvest data. And these models do a pretty good job estimating current fish biomass in line with data from the literature. And so we projected them back to 1850. Both models gave kind of similar biomass, and so we took the mean. And finally, for mammals, we used species-specific global surveys for the majority of the 126 marine mammal species. Mostly this data was drawn from IUCN, also some 250 published sources, many of which are, again, these are reconstructions of biomass, pristine biomass, so we just use those data. So we checked that our estimates were in line with other published global estimates for these major groups. We actually considered 12 groups, but we split them into 5 because those are the 5 methods that we used. And we checked. We also tried to construct confidence intervals on those estimates. And because we're using very different methods for different groups, this was quite difficult, but we can get into those kinds of details if you're interested afterwards. But basically, we just wanted to kind of sanity check all our estimates. And so there's our kind of global coverage of the data points. We also had global coverage for the chlorophyll, fish process models, mammal surveys, put it all together to get global distribution of total marine biomass. And then that biomass was partitioned into different size classes, big order of magnitude size classes. We didn't want to get into making too many assumptions. Again, we're just trying to sort of test this hypothesis. And then we were able to construct the size spectrum. And so this is what it looks like based on our best estimates from bacteria to whales. And it looks quite consistent across the size spectrum. In fact, we were quite amazed when we saw this. I feel like I should just pause and let you marvel at its beauty, because it's like, I haven't seen anything like this in ecology. And maybe you're saying, well, we've known this for 50 years. So surely we've moved beyond marveling, but it's not really widely known. I mean, on one hand, this is potentially the largest scale pattern in nature. And yet on the other, up until late last year, there wasn't a single entry of the size spectrum on Wikipedia or any of its aliases, biomass spectrum, normalized abundance spectrum, Sheldon spectrum, not even referenced on another page. It's not mentioned in many ecology textbooks. And I don't remember learning it in my biology undergrad. Of course, I don't remember much of anything from my undergrad. But anyway, I would say it's not widely known, and yet it's this big, beautiful pattern. So I think it's kind of deserving of your marvel, not this figure per se. We could have done it, drawn it in lots of ways, but the fact that this pattern exists in nature, I think is remarkable. The slope is very near -1, which is what we'd expect. Count is inverse to size, so that when we multiply count and size, we obtain this sort of fairly even distribution of biomass. And so I'll just quickly describe what this pattern is this plot is showing. The hatched lines are down to the depth of the ocean, and we weren't as confident in these estimates because there's a far less data available at depth. And then the colored bars of the upper sort of 200 meters sunlit portion of the ocean. And so, and then these are our error bars. You can see they're really large error bars, but yeah. And then if there are any exceptions to this, sort of 1 gigaton per 1 order of magnitude size class, which is what sort of this line would show, those exceptions would be indeed bacteria themselves down here being slightly above, maybe twofold greater than everything else, or large mammals. And in fact, these are mostly whales because they're really the largest mammals. So we could say that Sheldon et al. Were right, except for bacteria and whales themselves. But I don't know if we're going to nitpick on that. I would say Sheldon was very close to being right. So so well done, Sheldon, according to our study at least. And so then once we had this sort of these pristine estimates, we wanted to estimate how has that changed up until the present day. And so we used prior global syntheses of fish loss from stock assessments and ecosystem models. We basically took what other people had reported, and we wanted to kind of put it in the context of the size spectrum, which allows this sort of holistic view of marine biomass. And then we wanted to also contrast that with estimates from climate change projections up to 2100. And those are really extreme projections based on RCP 8.5. But we just wanted to kind of have, an extreme scenario compared to current day fishing impacts to sort of see where they sit related to, in reference to each other. So we know that there's been, a ton of fishing, maybe a 4-fold increase in fishing since over the past 70 years, but most of that has been on the very large size classes. As you can see, anything above 10 grams has been really hard hit. And that kind of progresses to larger sizes. Compare fishing to climate projections. And again, this is under a sort of extreme scenario. And you see that fishing has already had a far greater impact than even the most dire projections, as far as we can tell. This isn't us saying this. This is other people saying this. We're just putting it on the same plot to get perspective on it. And the effect this has on the size spectrum is to take something that may have looked like this pristine biomass spectrum, and turn it into something like this, where we're sort of lopping off a considerable amount of the upper 1/3 of the spectrum. And so I'll just maybe summarize with this short video all we've said. Basically, we took water samples, we took satellite imagery, process models, global species surveys, and a variety of other data sources to estimate the global distribution of biomass density, which we then partitioned into size classes of 5 major groups. And based on these estimates, we constructed the pristine sort of pre-1850 biomass spectrum, which we found to be surprisingly even. But comparing that to today, fishing and whaling have significantly impacted larger size classes, and I would say altered one of life's largest scale patterns. So that's where we can conclude. And I guess we don't know all the implications that this alteration might have, but it appears to have a massive change to energy flow. I'm not sure about the origin of this pattern. There's been lots of theory, perhaps by people even in this room, or not in this room, but in listening right now. But I think a better understanding of the origin can help to understand the impacts that these changes might have. And so I see this kind of discussion could go in two directions, depending on where you folks lean, whether that's towards applied or pure. We could try to talk about some of the implications, or we could talk about maybe the theoretical origins. And so that's all I've got. But before I take questions, I should just say that when Maria first asked me to give this talk, she informed me that there was one rule, and that's that there's no such thing as a stupid question. And I was hoping we might extend that to answers. So if I give you a dumb answer, it's not a dumb answer. But anyway, I'll do my best. Thank you.